During the lecture, it's been shown that the main equations which define the dynamics of the Solow growth model can be stated as follows. The first equation is the equation for the dynamics of capital, K dot, which equals to S times Y, which is the output per unit of effective labor, minus N plus G plus delta times K, and this is the equation which defines the dynamics of the capital, which is a change of capital K dot, and it's been said that the equilibrium of the Solow growth model appears when the K dot is set to 0. Then we can write the following equation as Y equals to N plus G plus delta times K, and for Y we can substitute the production function. The production function in its baseline can be very simple. Y can equal to K to the power of small alpha, and then we can write S times K to the power of alpha equal to N plus G plus delta times K. And we can now solve this equation for K. And if we do it, we obtain the equation for optimal level of capital, which we denote as K star. And the equation K star equals to S, which is a savings rate, over N plus G plus delta to the power of 1 over 1 minus alpha. And because output is simply the capital to the power of alpha, then the optimal output is simply substitution of K star in this equation of the production function, and the Y star simply equals to S over N plus G plus delta to the power of alpha over 1 minus alpha. And this is the condition for the optimal level of output per unit of effective labor, which comes from the Solow growth model. And if we have this kind of prediction of our theoretical model, then our main task is whether the output, the actual output of countries over the world really corresponds to the output which is predicted by the Solow growth model, in particular by this key equation. So the first part of today's session will be a derivation of a so-called cross-country growth regression, and we will basically follow the approach by the Mankiw, Romer, and Weil from their paper from 1992, who pioneered the empirical research in economic growth, and who present a way how to verify whether the outcomes of the Solow growth model can be supported by the empirical data. Here you can see what are the main steps in the empirical verification. First, we derive the equilibrium level of output per capita. Here, in our equations, we have the equilibrium level per unit of effective labor. Recall that small y equal to big Y, which is the overall output over AL. However, in a data on economic growth, for example, in Penwold table, we have values for Y over L, which is basically the output per capita, and then we'll try to linearize this expression so that we can take this equation to the OLS estimation. So what are the main steps which we are doing? First, as I recall, the data are available for output per capita and not for output per unit of effective labor. So our first step starts that we need to multiply this equation for optimal output by A to obtain the expression for output per capita instead of output per unit of effective labor. It is pretty straightforward. So the first step, let me denote this equation by star. The first step is simply multiplication of the equation star by a. So we multiply both equations, both sides of the equation. So when we had on the left-hand side y over al and multiply it by a, then on the left-hand side we have simply output per capita y over l. And right-hand side, this is something what we can simply rewrite as s over n plus g plus delta to the power of alpha over 1 minus alpha times a. And output is at time t, L is at time t, the savings rate is simply parameter, these are parameters as well, these are parameters as well, and a evolves over time, so it is a function of time. Then here we have a AT, however we cannot really observe the values of AT. This is some level of technology, but we cannot find a level of technological progress in any tables, so this variable is in fact unobservable. And what we know about this variable? We know about this variable that the values AT, that the AT is simply growing over time. And using properties of differential equation, we can express the growth of the variable AT using initial condition denoted as A0 and exponential to the power of gt. And g is the growth rate of technology or productivity. And what we can do right now is that we can basically substitute this expression for AT into the equation 1, and we can so obtain a second step equation, and in the second step our equation becomes YT over LT equals to the same thing as before, that means S over N plus G plus delta to the power of alpha over 1 minus alpha times A0 e to the power of gt. You might now ask where this expression A0 times e to the power of jt came from. So let me briefly explain. We can assume that our technology AT has some growth rate gt, and how we can express the growth rate? We can basically express the growth rate as a change in technology over the technology itself. So this is our growth rate. And if we see here the A dot expression, which is a change of, which is the first derivative of AT, we can see that this is a simple differential equation. Anywhere there are simply some properties of differential equations, some definitions, which state that 1 over x times dot x, these are some rules of derivations, equal to derivation of logarithm of x over t. And if we now know that the derivation of a logarithm of x equals to x dot over x, we can just use it for solution of this simple differential equation. We can basically integrate both sides of the equation. And if we integrate this side of the equation using this definition, we basically obtain a logarithm of a t which equals to the integration of the left-hand side of this equation, so we can just put it on the other side for convenience, and the integration of gt is simply g times t plus some constant. And here it is in logarithm, but here in all other equations we have a in absolute values, so we take exponential now of both sides of the equation. And if we take exponential of both sides of the equation, we obtain at equal to e to the power of gt, which is exactly here, times some constant, which can be basically this initial condition a0. And that's exactly the expression which we are using here in equation 2 instead of at. And now when we understand the equation at, we can move forward to equation 3, and the equation 3 is basically a linearized version of equation 2. And how to linearize an equation? We see that here is multiplication, so to linearize it, we basically take logarithm of equation 2. So first, there will be logarithm of our output per capita at time t equals 2. And now here we have this great long expression. So we have here basically logarithm of a0 plus logarithm of e to the power of gt, this is simply gt, plus and now logarithm of this expression will lead to alpha over 1 minus alpha logarithm of s minus alpha over 1 minus alpha logarithm of n plus g plus delta. And this now looks like an expression of an equation which can be estimated because it is a linear functional form. We need still to make a couple of small tricks, but those tricks are pretty straightforward. So first of all, I've told that the value of the technology is unobserved, and here we have a0, so we cannot really have any data for it. But this one is basically, it's some initial condition, so the initial condition is constant, and here we don't see any regression constant, so this can be captured by a constant in a regression equation. Similar issue is related to the g times t expression. We will take this regression to cross-sectional data, and here we have some number of years for which we are studying economic growth. In our case, it will be 20 years, so t would simply equal to 20, which is constant for all countries, and g is again some constant number. And so as a consequence, g times t is again some constant, and as a consequence, both of those terms cancel out into regression constant, into a constant in a regression, which will have on the left-hand side, where our dependent variable would be the logarithm of output per capita, where will be constant plus, and here will be, let's denote it as a c0 as a constant. Here will be the first coefficient c1 times logarithm of the savings rate, and here will be c2. It will be basically the same value in opposite value, but first we estimate the unrestricted regression, c2 times logarithm of n plus g plus delta plus UI T. And this is our regression equation, which we can estimate using the data which we have available. And this is a basic form of something what we call cross-country growth regression.